It is section 16.9, the divergence theorem. Earlier, for two-dimensional vector fields, we considered vector forms of Green's theorem, including this formula. The integral is along a closed curve, positively oriented. Now the integrand is the normal component of the vector field. The integral is the same as this area integral. Now integrand is divergence of the vector field. The divergence theorem is a generalization of this formula. So now we'll deal with surface integrals versus volume integrals. Let's see the theorem. E is a simple solid region in 3D, and S is the boundary of E given with a positive outward orientation. And the vector field has continuous partial derivatives on an open region containing E. Then the surface integral of the vector field can be evaluated by using this volume integral. Now the integrand is divergence of F. So this simple expansion from this one. This is curve and area. That is a surface, and that is volume. Okay. S is surface parameterized by R. Then we know that now f ds, the surface integral of the vector field, that's in definition we have that along with known identity for n, and ds we reach at that integral. Now we can evaluate the integral over D, which is a flat two-dimensional region. This formula can be used for every surface, whether or not it is closed. And now when it is closed, we can use this formula. And the theorem can be also used for unclosed surfaces. For example, some portion is like some paraboloid, and then original surface only the side. Then because this bottom is simple, we may consider its closed surface, and using divergence theorem we can get the surface integral easily, and then this portion of the contribution can be subtracted. So in this way you can use the divergence theorem. Okay. This problem is a revisit. Find the flux of z(yx), the vector field, over unit sphere. The flux is now integral over S and vector field and ds, right? Now this is close to the surface, the unit sphere. So we can use the divergence theorem, and we see the whole solid is now E. Then divergence of F can be used here. X derivative 0, Y derivative is 1, Z derivative is 0. So the 0 plus 1 plus 0, and that is dV. So it is the same as volume of E. It's a sphere of radius 1, so it is 4/3 pi r cubed. R is 1, so that is the answer. Quite simple. Find the flux of F across S. Now, flux I'm sorry, that is a vector field. Vector field is defined in this way, and S is the surface of a solid bounded by the paraboloid and z equal 4. Let's try to visualize the surface and solid inside. So that is paraboloid and z equal 4, so that it's cut at 4, so the height is now 4. That is the solid, and we consider as every top and side together. So the flux is integral over S and F dot ds, which is the same as now here E inside the volume integral, that is divergence of F and dv. Okay, let's see the divergence. Okay, x derivative of the first component, which must be y squared. Now for y derivative, that is 0. And now z derivative of this one, which must be x squared. Okay. Now we have to get this triple integral. What is the technique for the triple integral? Okay, first you have to separate the three-dimensional region into two-dimension and one orthogonal direction. 1A you can do easily as that it can be projected onto the plane. Then the bottom is circle of radius 2, because that one from here and from here z equal 4. Then on the top, that same as x squared plus y squared equals 4. So that is exactly circle of radius 2. We may consider this one is d, and the volume can be accessed for each xy from bottom z to top z, right? Okay, so let's do it. So that is same as double integral over d, that is bottom. For each point on d, bottom, z is on the surface here. That is same as from here, so that is x squared plus y squared. The top z is 4, right? And the integrand is x squared plus y squared. We do first integral along z direction and later area integral. Okay, this is z independent, so we can get it quite easily. Double integral over d, and that's integrand x squared plus y squared. And here we have length, so 4 minus x squared plus y squared, and dA. Right? D is a polar region. Angle is from 0 to 2 pi, whole circulation, and R is from 0 to 2. So that is same as from 0 to 2 pi. R is from 0 to 2. The first one is R squared, and second one is 4 minus R squared. And we need extra R for this change of variable, and dr d theta. Okay. This is a theta independent, so it is can get theta integral 2 pi immediately, and that is now integral. Okay, let's rewrite this one. And r cubed, so the 4 r cubed minus r to the 5, and we make r integration. Okay, then that is 2 pi. And that is now r to the 4 minus 1 over 6 r to the 6 and 0 to 2. Okay, there's 2 pi. When it is 2, then there's 16, minus, okay, and when that is 64 divided by 6, which is 32 over 3. Okay. So here we have 2 pi, and that is 48 over 3, so that 16 over 3. So we can reach at the right answer. Okay, that's the final answer. The divergence theorem is given as here. So for closed surface, the vector field integration is now volume integral of the divergence. But this one, by definition, is the same as that. So that is f dot s. The reason we are considering this one is here. Use the divergence theorem to evaluate this integral where S is the unit sphere. Okay. Now, this is not a form of this one, but it looks like this one. If we consider this portion as f dot n, then now if we can find n, then we can find f. Okay, let's try to do that, right? So f dot n is given. Then for sphere, what is the unit outer vector for that is sphere? Now, okay, like that. If we choose one point here, then this unit vector, outer normal vector, must be here now. Okay, that is x and y and z, right? But we can check it quite easily, the length of that one. So norm, which is same as square root of x squared plus y squared plus z squared. But already we know that that is 1, so that it is 1. So this one is already unit normal vector, right? So we found the unit normal vector in this way. So let's rewrite this one here. F dot n. Okay. Okay, first let's write down n first. Okay, here n is now x, y, and z. Now here f dot n, they're the same as x squared plus 2y squared and plus z e to the x. Now from these two, we have to get f, that is a three-dimensional vector field. Now here n and f, so we need a component here so that after multiplication we may get some part of this one. So there is x here, this one includes x, so that let's try to put here x. Then this component, that one, multiplication will be x squared. The same way, now we have 2y squared, we have 1y, so let's try to choose 2y. Then these two product will become this one. Now we have z, okay, we put here e to the x, then these two product will make here z e to the x. Okay, we found the vector field. Now from here, we can get divergence of f. That is 1 plus 2 plus, now there is 0. 1, 2, x derivative, y derivative, z derivative. So we have, there is a 3. Okay. So the given integral must be same as now volume integral over E and divergence of f, which is 3 dv. So that is same as 3 times of volume of E. For this one, this is a sphere of radius 1, so that here the volume is 4 over 3 pi r cubed. R is 1, so we have that. So eventually we can get 4 pi, which is the final answer. Okay? Not so much complicated. Okay. Now we assume S and F satisfy the conditions of the divergence theorem, and functions have all required continuous partial derivatives, first or second order. Let's prove this claim. Okay, A dot n and surface integral for closed surface equals 0 for any constant vector A. Is it true? That is exactly here. If we are using divergence theorem right now, F is A. If you try to take divergence of the constant vector field, then that must be 0. So that one is now divergence of A equals 0. So that by using the divergence theorem, it must be 0. Now, how about the part 2? For this one, we focus on this portion only. Okay, then that is same as now the volume integral of divergence of F. F is given in this way. So x derivative, y derivative, z derivative, summation must be 3, right? So that it is the same as 3 times of volume of E. Okay, this portion is 3 times of volume of E, so that along with 1/3 is correct, right? Now, how about this one? Curl of F, we try to get the surface integral for curl of F, and that must be 0. Why? If you are using divergence theorem, then that term must be same as the volume integral over E and divergence of curl of F. Okay? For vector field having second order partial derivatives, continuous second order partial derivatives, and this one is always 0. Curl and divergence is 0. That can be proved by using the clarity theorem. So that is 0. So we have 0. Okay? Curl. So in divergence theorem, you have divergence curl of F, which is 0 when it has continuous second order partial derivatives. Okay. Okay, that's the end of section, and that's the end of lectures for Calculus 4. Thank you.